February 21st, 1935. A frozen field in Daventry, England. A BBC radio transmitter hums in the background. Robert Watson Watt stands beside a van equipped with makeshift equipment that looks more like a science fair project than military technology. His assistant, Arnold Wilkins, watches a cathode ray tube, its green glow reflecting off his glasses. Above them, an RAF bomber flies a predetermined course. Then it happens. A blip appears on the screen. Just a tiny spike in the signal. But that spike would change the course of human history. What Watson Watt didn't know that cold morning was that he'd just demonstrated. The technology that would expose every Nazi bomber before it. Crossed the English Channel, lead to one of the most daring commando raids of World War II, and ultimately save Britain from invasion. This is the story of radar, the invisible shield that won the war before most people even knew it existed. But here's the thing that makes this story truly controversial. Both sides had radar. The Germans actually had better radar in some ways. So why did Britain survive while German cities burned? The answer isn't just about technology. It's about secrets, sacrifice, and decisions that would haunt their makers for decades. Let's go back to where this all started, because the origin of radar begins with a myth and a desperate fear that gripped 1930s Britain. The year is 1934. Adolf Hitler has been in power for just over a year. German rearmament is an open secret, and in Britain there's panic about something called the death ray. Newspapers are filled with speculation about Nazi scientists developing a weapon that could kill pilots in their cockpits, or blow planes out of the sky with directed energy beams. It sounds like science fiction, but the British Air Ministry is taking it seriously enough to investigate. They turn to Robert Watson Watt, superintendent of the Radio Research Station. His job? Determine if a death ray is actually possible. Watson Watt does the math and delivers bad news. A death ray powerful enough to boil a liter of water at a distance would require energy equivalent to a small power station. It's fantasy. But then Watson Watt says something that changes everything. If you can't kill the pilot, maybe you can see the plane. Radio waves bounce off metal objects. Everyone knew this. It was an annoyance for radio engineers because aircraft flying overhead created interference. But Watson Watt realized this wasn't a bug. It was a feature. If you could measure that interference precisely, you could detect aircraft at a distance. You could see them coming. This is February 1935. Hitler has just announced Germany is rebuilding the Luftwaffe in direct violation of the Treaty of Versailles. Britain has about 1,600 aircraft. Germany is building toward 2,500 and growing fast. The strategic bombers that had terrorized cities in World War I are now faster, carry bigger payloads, and can strike with little warning. The nightmare scenario keeps military planners awake at night. Hundreds of German bombers appearing over London with just minutes of warning. By the time fighters scrambled and climbed to altitude, the bombs would already be falling. Britain's entire defensive strategy was built on the assumption they'd need thousands of fighters and massive numbers of anti-aircraft guns to create an effective defense. The cost would be astronomical. The likelihood of success? Uncertain. Watson Watt's demonstration in that frozen field offered something different. Not a weapon, but information. Time. The ability to see the enemy while they were still forming up over France. Time to scramble fighters. Time to guide them to exact intercept points. Time to win. The Air Ministry immediately classified the project under the bland code name RDF, Radio Direction Finding, a name deliberately chosen to sound boring and routine. They gave Watson Watt funding and a remote site on the Suffolk coast called Bawdsey Manor. His mission? Build a network of radar stations before war arrived. What he built would become known as Chain Home, and it was magnificent in its ugliness. Imagine approaching the British coast in 1938. Sprouting from the cliffs are wooden towers, some over 350 feet tall, taller than the Statue of Liberty. They look like giant derricks, like something from an oil field, bristling with antenna arrays. They're spaced roughly 20 miles apart along the entire eastern and southern coast of England. Each station has transmitter towers and shorter receiver towers, working together to ping the skies with radio waves and listen for echoes. The system is crude by modern standards. It operates on long wavelengths, which means large antennas and relatively low resolution. It can't determine altitude accurately, only height within broad bands. It can't detect aircraft flying very low, below about 500 feet. The displays aren't even electronic. Operators plot contacts on paper maps, using information called out by other operators watching cathode ray tubes. But it works. By 1939, Chain Home can detect aircraft at ranges up to 120 miles. More importantly, it's connected to a revolutionary command and control system devised by Air Chief Marshal Hugh Dowding. Here's what makes Dowding's system revolutionary. Radar detection is only the beginning. Information flows from Chain Home stations to Fighter Command headquarters and regional operations rooms. In these operations rooms, military personnel, many of them women from the Women's Auxiliary Air Force, plot contacts on enormous maps. They track every raid in real time. Controllers can see the developing battle from a God's eye view, and vector fighters to precise intercept points using radio. For the first time in history, the defense has the advantage. Fighters don't need to fly standing patrols, burning fuel and exhausting pilots. They can wait on the ground and scramble only when raids approach. They can be guided directly to incoming bombers rather than searching blindly. A single fighter squadron, used efficiently with radar guidance, can do the work of 3 or 4 squadrons flying blind. Germany has nothing like this. The Luftwaffe has radar, yes. They've developed the Freya early warning system and the Würzburg tracking radar. On a purely technical level, Würzburg is actually superior to anything Britain has, more accurate, more precise. But the Germans never integrate radar into a comprehensive air defense network like Chain Home and the Dowding system. They see radar as a tactical tool, not the foundation of an entire defensive strategy. This philosophical difference in how radar is used, will decide the Battle of Britain. Summer 1940. France has fallen in 6 weeks. The British Expeditionary Force has evacuated from Dunkirk, leaving behind nearly all its heavy equipment. Britain stands alone. Hitler issues Directive No. 16, the order to prepare Operation Sea Lion, the invasion of Britain. But first, the Luftwaffe must destroy the Royal Air Force. Hermann Göring, commander of the Luftwaffe, is confident. He has roughly 2,800 aircraft. Britain has about 900 fighters. The math seems simple. What Göring doesn't understand is that he's not fighting just 900 fighters. He's fighting 900 fighters multiplied by the force multiplication of radar. The Battle of Britain begins in earnest on July 10, 1940. German bombers, escorted by fighters, cross the Channel to attack shipping, ports, and later, RAF airfields. Every time they form up over France, Chain Home sees them. Every time they cross the coast, operators track them. RAF fighters, guided by radio from operations rooms, appear as if by magic at the exact right altitude and position to intercept. From the German perspective, it's baffling and frustrating. They know the British have radar, they can see the towers from across the Channel, but they don't understand how effective it is, how it's being used. Luftwaffe intelligence consistently overestimates British fighter losses. They think they're grinding down the RAF. They're not. Here's a crucial moment in the battle that perfectly illustrates the power of the system. On August 15, 1940, the Luftwaffe launches its largest operation yet, attacks across the entire front, including a large raid from Norway targeting northern England. It's a coordinated assault designed to overwhelm British defenses. But Chainholm detects the Norwegian raid while it's still over the North Sea, nearly 100 miles away. Fighters have time to climb to altitude and position themselves perfectly. The raid is mauled. The Luftwaffe loses 75 aircraft that day compared to 34 for the RAF. The mathematics of attrition are working in Britain's favor, the exact opposite of what Göring expected. And there's another factor. British pilots who bail out over England can return to combat if they survive. German pilots who bail out become prisoners of war. Chainholm isn't just detecting aircraft, it's preserving Britain's most valuable resource, trained pilots. By late September, the Luftwaffe switches to nighttime bombing of cities. The Blitz. They can't defeat the RAF. Operation Sea Lion is postponed indefinitely. Britain has won the Battle of Britain, and radar is the reason why. Winston Churchill will later write, "The outstanding achievement of the Royal Air Force was the defeat of the German Air Force in the Battle of Britain. But if radar had not been developed to the extent it was, we should have had to have many more fighter squadrons to provide adequate defense. And these squadrons would have had to be flown much more frequently, at a heavy cost in pilots. But while Britain is celebrating its survival, a brilliant physicist in British intelligence is starting to piece together the true extent of German radar capabilities, and what he discovers will lead to one of the most audacious raids of the war. His name is Reginald Victor Jones, though everyone calls him RV. He's 28 years old when war breaks out, a physicist recruited into intelligence specifically to understand German scientific developments. He's given the bland title Assistant Director of Intelligence Science, but his job is anything but bland. He's responsible for figuring out every scientific trick the Germans might use and developing countermeasures. Jones is brilliant, methodical, and imaginative in equal measure. He approaches intelligence like a physics problem, gathering data, forming hypotheses, testing them against new evidence. And in 1940, he's working on a puzzle that's costing British bombers their lives. RAF bombers attacking Germany at night are being shot down in alarming numbers, not by searchlights and visual targeting, which would be understandable, but apparently by something else. Pilots report German night fighters appearing out of darkness with uncanny accuracy. Anti-aircraft fire is too accurate for the limited information German ground observers should have. Something is guiding them. Jones suspects radar. He's right, but he needs proof. He needs to understand exactly what kind of radar and how it's being used. British intelligence has already identified 2 German radar systems from intercepted communications and photo reconnaissance, Freya and Würzburg. But the details are murky. Then Jones gets a break. A German bomber is shot down over Britain with radar equipment aboard. Analysis reveals it's more sophisticated than expected. Around the same time, a source in occupied Europe provides crucial information about German radar installations. Aerial reconnaissance begins photographing the French coast systematically, looking for radar sites. In November 1941, a reconnaissance Spitfire brings back photos of a cliff-top site near the French village of Bruneval. Photo interpreters spot something that makes Jones's pulse quicken. A Würzburg radar installation. It's sitting exposed on the cliff, close to the coast, and theoretically accessible. Jones proposes something audacious. Raid the site, dismantle the radar, and steal it. Bring it back to Britain for analysis. The military thinks he's insane. Bruneval is occupied France. The site is defended. It's winter. The operation would require paratroopers, specialized equipment, and perfect timing. The chances of success seem minimal, but the potential intelligence gain is enormous. British scientists need to understand exactly how Würzburg works to develop effective countermeasures. Every night, RAF bombers are dying. This could save them. The plan is approved. The operation is codenamed Biting February 27, 1942, just before midnight. 12 Armstrong Whitworth-Whitley bombers lumber through the darkness over the English Channel. Inside their fuselages, 120 men of C Company, 2nd Parachute Battalion sit in the cramped spaces, checking equipment. Among them is Flight Sergeant Charles Cox, an RAF radar specialist. His job is to identify the components that matter, quickly dismantle what can be moved, and photograph everything else. They're dropping into the unknown. Intelligence suggests about 100 German troops defend the area, but the exact number and alert status are uncertain. The paratroopers will have to secure the radar installation, hold it long enough for Cox to do his work, then fight their way to the beach where landing craft from the Royal Navy will extract them. Simple in concept, nightmarish in execution. The aircraft cross the French coast. Green lights flash. Men jump into the darkness. The wind scatters them across the drop zone. Some land in trees, others in gardens of the village itself. The careful plan immediately dissolves into chaos, as all plans do upon contact with reality. But training takes over. Groups rally and move toward objectives. The assault group under Lieutenant Ewan Charteris reaches the radar site and finds it lightly guarded. A brief, fierce firefight erupts. The Germans are overwhelmed. The radar is secured. Cox rushes forward with his tools. The Würzburg dish towers above him, a parabolic reflector about 10 feet in diameter, rotating on a mobile platform. It's more sophisticated than anyone expected. Cox begins dismantling key components, working by flashlight while gunfire echoes around him. The transmitter unit, the receiver, control mechanisms. Other soldiers photograph everything, wide shots, detailed shots, labels on equipment. Every second counts because German reinforcements are coming. Cox realizes quickly they can't take the whole radar. It's too heavy, too complex. He focuses on the most critical components: the receiver unit, some control equipment, and detailed photographs of everything else. Meanwhile, other paratroops are fighting running battles with German troops converging on the site. The extraction is supposed to happen at a beach below the cliff. The paratroopers fight their way down steep paths, carrying wounded comrades and the precious radar components. German fire follows them. They reach the beach and find it empty. The landing craft are late. For desperate minutes, the paratroopers are trapped on the beach, exposed, taking casualties. Then engines roar over the water. Landing craft surge onto the beach. Men pile aboard under fire, hauling radar components and wounded. The craft reverse and race into the darkness. Behind them, Bruneval Lighthouse suddenly illuminates, spotlighting the retreating boats. German machine guns open up. Bullets stitch the water. But they're away. By dawn, the raiders are back in England. The butcher's bill: 2 dead, 6 wounded, 7 missing. But in the holds of those landing craft are pieces of Nazi Germany's most advanced radar system. The Würzburg components are rushed to the Telecommunications Research Establishment at Malvern. British scientists swarm over them like archaeologists examining artifacts from an alien civilization. What they discover is both impressive and troubling. The Würzburg radar operates at a wavelength of 53 centimeters, much shorter than Chain-Home's meters-long waves. This gives it far better accuracy and resolution. It can track individual aircraft with precision good enough to guide anti-aircraft fire or night fighters to within visual range of bombers. The engineering is excellent, compact, mobile, reliable. But there's good news, too. The system operates at a frequency that can be jammed. British scientists immediately begin developing countermeasures. Within months, they've created electronic jamming equipment that can blind Würzburg radars. The code word for these jammers is mandrel. More importantly, the raid proves that aggressive intelligence gathering works. It validates R.V. Jones's approach of not just analyzing the enemy from a distance, but actively going out and taking what you need to know. Other raids will follow this model. The intelligence gained at Bruneval directly contributes to saving hundreds of bombers and thousands of aircrew in the coming years. But technology is evolving on both sides, and Britain is about to deploy a radar innovation that will prove so revolutionary it's been called the invention that won the war. Not Chain-Home, something smaller, more powerful, and absolutely secret. 40 Fourn, University of Birmingham. Two physicists, John Randall and Harry Boot, are working in a makeshift laboratory on a problem that's been frustrating radar engineers since the beginning. Radar works by sending out pulses of radio energy and detecting reflections. The stronger the pulse, the longer the range and better the resolution. But generating powerful radio pulses at short wavelengths, the kind needed for precise targeting, requires enormous power supplies and produces weak signals. What's needed is a way to generate powerful microwave pulses in a compact package. The theory exists, but the engineering has defeated everyone who's tried. Randall and Boot decide to try a radical redesign of a device called a magnetron, using a concept called resonant cavities. In February 1940, they test their first prototype. It produces 400 watts of microwave power, far more than any previous device of its size. They refine the design. By May, they've built a cavity magnetron that produces kilowatts of power at a wavelength of 10 centimeters. It's a revolution in a copper cylinder about the size of a grapefruit. The cavity magnetron makes possible radar systems that are smaller, lighter, and more precise than anything previously imaginable. It enables airborne radars that can detect submarines on the surface at night. It enables radar gun sights that can track enemy aircraft and automatically compute deflection. It enables ground mapping radars that let bombers navigate and identify targets through clouds and darkness. The technology is so valuable that Britain makes an unprecedented decision. In September 1940, at the height of the Battle of Britain, with invasion looming, the British government sends the cavity magnetron to the United States as part of the Tizard mission, a delegation offering Britain's most advanced technology in exchange for American industrial capacity to mass produce it. The Americans are stunned. According to accounts from the meeting, American scientists literally gasp when they see what the magnetron can do. It's years ahead of American radar development. Companies like Raytheon and Bell Labs immediately begin mass production. By 1941, cavity magnetron radars are rolling off assembly lines by the thousands. This technology flows into a dozen applications. Airborne intercept radars that let night fighters hunt bombers in total darkness. Naval surface search radars that can spot periscopes and surfaced submarines. The H-2S ground mapping radar that lets British bombers navigate to and identify targets in Germany, even through cloud cover. Every advance saves lives and increases effectiveness. But technology cuts both ways, and German scientists are not sitting idle. By 1943, both sides have sophisticated radar systems. The Germans have improved their Würzburg and Freya networks and added the massive Mammoth early warning radars that can detect formations at extreme range. They've deployed airborne radars on night fighters that hunt British bombers with increasing success. The Battle of the Ruhr in 1943 costs Bomber Command horrific casualties, partially due to increasingly effective German radar-directed defenses. RAF losses are climbing toward unsustainable levels. In some raids, 10% of bombers don't return. Do that math over a 30-mission tour, and most aircrew won't survive. Something has to change. British scientists have a solution, but it's controversial. It's been ready for over a year, but it's been forbidden to use it because of fear that Germany will copy it and use it against Britain's own radars. The solution is called window. Window is absurdly simple. Thin strips of aluminum foil cut to precise lengths corresponding to the wavelength of German radar. Drop massive quantities from bombers, and each strip reflects radar waves, creating false echoes. To radar operators on the ground, one bomber becomes 100. The radar screens turn into a blizzard of contacts impossible to sort. Gun-laying radars lose track. Night fighter controllers can't vector their aircraft to targets. The entire radar-directed defense network becomes useless. The concept isn't new. German scientists know about it too. They call it Düppel. Both sides have it ready. Neither side wants to be the first to use it, because once it's deployed, the other side will copy it immediately. It's a standoff based on mutual fear of escalation. But by mid-1943, Bomber Command's losses force a decision. The Battle of Hamburg is planned for late July, a massive incendiary raid designed to create a firestorm in Germany's second-largest city. It will be the first test of window. The night of July 24th, 1943. 791 RAF bombers take off for Hamburg. As they approach the German coast, crews begin throwing bundles of window out of chutes in the aircraft fuselages. Thousands of aluminum strips flutter into the night sky, each one creating a radar return. On the ground, German radar operators watch their screens dissolve into chaos. Where there should be distinct blips representing individual aircraft, there's just a solid mass of returns filling the scopes. The carefully calibrated system of detection, tracking, and interception falls apart. Night fighters circle uselessly, receiving contradictory vectors from confused controllers. Anti-aircraft batteries fire blind into the mass of contacts, wasting ammunition. The bombers reach Hamburg and deliver their attack with unusual accuracy, also aided by the H-2S ground mapping radar that lets them identify the city despite cloud cover. The raid creates a firestorm that kills over 40,000 people and destroys much of the city. It's one of the most devastating air raids of the war. Over the following week, Bomber Command returns 3 more times. Each time, window protects them. RAF losses during the Hamburg raids are a fraction of what they'd been on recent operations. The system works, but as predicted, Germany immediately begins deploying their own version against British radars. The technology cannot be undeployed. It's out, and both sides must adapt. German radar operators learn to look for patterns in the chaos. New radars operating at different frequencies are deployed. The electronic warfare arms race accelerates. This pattern of measure and countermeasure, of innovation met with counter-innovation, defines the radar war for the rest of the conflict. Neither side ever gains a permanent advantage. Every breakthrough is eventually countered, leading to new breakthroughs. Let's step back and look at what made British radar ultimately more effective than German radar, because it's not just about technology. Both sides had good technology. The Germans actually deployed some innovations first. So why did Britain's radar system prove more decisive? First, integration. Britain built Chain Home as part of a comprehensive system that included communications networks, command centers, and fighter control. It was never just about detecting aircraft. It was about creating a responsive defense network that could process information and direct forces efficiently. Germany deployed radar stations but never created an equivalent integrated air defense network with the same level of coordination. Second, philosophy. British leadership, particularly Hugh Dowding, understood that radar's value wasn't just tactical, but strategic. It changed the fundamental mathematics of air defense, making it possible to defend Britain with far fewer fighters than conventional wisdom suggested. Germany saw radar as a useful tool, but continued to rely primarily on numbers and aggressive tactics. Third, scientific intelligence. The work of people like R.V. Jones gave Britain insights into German capabilities that allowed for targeted countermeasures. Operations like the Bruneville raid weren't just propaganda victories, they provided actionable intelligence that saved lives. Germany had competent intelligence services but never developed the same focus on scientific and technical intelligence gathering. Fourth, and perhaps most important, sharing. The Tizard mission's decision to give the cavity magnetron to the United States brought American industrial might into the radar game. By 1943, American factories were producing radar systems in quantities Germany couldn't match. That same spirit of cooperation meant British and American scientists could collaborate, accelerating innovation on both sides. Finally, there's a human element. The people operating British radar systems, from the scientists designing them to the Women's Auxiliary Air Force plotters, tracking raids in operations rooms, were fighting for their homes. They saw the bombers coming for British cities. That gave the work an urgency and dedication that translated into effectiveness. None of this is to diminish German achievements. They created excellent radar technology. But technology alone doesn't win wars. It's how you use it, how you integrate it into doctrine and strategy, how you adapt when the enemy counters it. In that larger contest, Britain simply did it better. As the war progresses, radar becomes ubiquitous. By 1944, virtually every military aircraft has some form of radar equipment aboard. Destroyers and submarines hunt each other with radar and sonar. Artillery uses radar to track shells in flight and compute corrections. Even individual soldiers carry small radar units that can detect approaching vehicles or aircraft. The D-Day invasion in June 1944 showcases how far the technology has evolved. Allied ships use radar to navigate in the pre-dawn darkness and control naval gunfire support. Aircraft use radar to identify drop zones and bombing targets despite cloud cover. German coastal radars, which should have provided early warning, are blinded by massive jamming operations and window drops. The entire invasion is coordinated using radio and radar technologies that didn't exist 6 years earlier. By the time Germany surrenders in May 1945, radar has been so thoroughly integrated into military operations that it's almost invisible, taken for granted as a basic capability, rather than the revolutionary technology it was in. 1940. The post-war world will inherit this technology and transform it in ways Watson Watt couldn't have imagined. But there's a darker side to this story that we need to confront. The strategic bombing campaign that radar enabled killed hundreds of thousands of civilians. The firestorm in Hamburg wasn't the only one. Dresden, Tokyo, and dozens of other cities burned. The precision that radar promised often failed to materialize in practice, and even when it worked. The targets frequently included residential areas. Commanders like Arthur Harris, head of RAF Bomber Command, argued that terror bombing would break German morale and shorten the war. It didn't. German production actually increased through 1944 despite the bombing. The moral calculus of terror bombing, whether it was justified as a military necessity or whether it crossed ethical lines into war crime, continues to be debated by historians. Radar made these campaigns possible by letting bombers navigate to targets at night and through clouds. Without radar, the strategic bombing campaign as it was conducted would have been impossible. Does that make radar scientists complicit in the deaths of civilians? It's an uncomfortable question without easy answers. The scientists involved had varied responses. Some, like Watson Watt, saw their work as defensive, protecting Britain from invasion. Others struggled with the implications as the war progressed. R.V. Jones wrote extensively in his memoirs about the ethical dimensions of his work, the weight of knowing that his intelligence led to operations that killed people. Technology is morally neutral. It's a tool, but the people who create and deploy technology bear responsibility for how it's used. The radar pioneers of World War II created something that saved Britain and contributed to defeating fascism. They also created something that enabled mass killing of civilians. Both things are true, and we diminish neither the achievement nor the tragedy by acknowledging both. After the war, radar technology explodes into civilian applications. Air traffic control systems use radar to track and separate commercial flights, making modern air travel possible. Weather radar helps predict storms and saves lives. Marine radar prevents collisions at sea. Police radar catches speeders. Radar astronomy maps the surfaces of planets and asteroids. Medical imaging technologies derive from radar innovations. The cavity magnetron ends up in kitchen microwave ovens, cooking dinner with the same technology that once tracked Nazi bombers. It's one of history's more ironic technology transfers. Watson Watt is knighted for his contributions to radar. He lives until 1973, long enough to see radar become so commonplace that people forget it was ever new. There's a famous story, possibly apocryphal, that he once received a speeding ticket from a radar gun and remarked, Had I known what you were going to do with it, I would never have invented it. R.V. Jones returns to academic life, becoming a professor of physics and writing Most Secret War, a memoir that's considered one of the finest intelligence books ever written. He's candid about successes and failures, and thoughtful about the ethical dimensions of scientific intelligence work. The radar operators, the plotters, the ground crew, the scientists, most of them return to ordinary life. Their contributions are classified for decades. When the full story of radar finally emerges in the 1970s and 80s, many of the key figures are already dead. The Women's Auxiliary Air Force personnel who plotted raids in operations rooms, whose work was as vital as any pilot's, received little recognition until recent years. This is often how history works. The visible heroes, the fighter pilots and commanders, get the glory. The invisible enablers, the ones who made victory possible, fade into footnotes. So what do we take from this story? What does radar's role in World War II teach us about technology, strategy, and human conflict? First, that invention and innovation are often born from desperation. Britain developed radar because they were terrified of German bombers and couldn't afford a conventional defense. Necessity drove innovation in ways peace never could have. Second, that technology alone is never enough. Germany had good radar and lost. Britain had good radar and won. The difference was in organization, doctrine, and how the technology was integrated into a larger system. This lesson remains relevant today as we grapple with artificial intelligence, cyber warfare, and other emerging technologies. Third, that information is power. Radar gave Britain time and awareness. It let them see the battle developing and respond efficiently. In modern terminology, it provided decision advantage. The side that knows more and knows it sooner has an enormous edge, regardless of raw numbers. Fourth, that secrecy is temporary, but consequences are permanent. The British delayed using Window for over a year because they feared Germany would copy it. When they finally deployed it, Germany copied it immediately, as expected. But hundreds of aircrew died in that year of delay. Sometimes the advantage of using a capability outweighs the advantage of keeping it secret. Fifth, that technology cannot be uninvented. Once radar existed, it proliferated. Once Window was deployed, both sides had to adapt to a world where radar could be jammed. The technology genie, once out of the bottle, doesn't go back in. This has implications for everything from nuclear weapons to genetic engineering to artificial intelligence. Finally, that the people who create transformative technology bear responsibility for thinking through its implications. Watson Watt created a defensive system that saved Britain. But that same system enabled bomber streams that incinerated cities. He didn't make the strategic decisions about how to use bombers, but his technology made those decisions possible. There's a responsibility there that can't be shirked. Today, radar is so ubiquitous that we barely notice it. Every commercial aircraft, every ship, every weather station, thousands of satellites orbiting above us, all using descendants of the technology developed in that desperate rush before World War II. The chain-home towers are mostly gone now, demolished as obsolete or fallen to decay. A few remain as monuments, towering rust-streaked memorials to a time when wooden scaffolding and crude electronics stood between Britain and invasion. The operations rooms where WAF, plotters tracked raids, have mostly been converted to museums. You can visit some of them and see the map tables, the status boards, the cramped spaces where teenage women calmly marked the approach of bombers that were coming to kill them. The technology has evolved beyond recognition. Modern phased-array radars bear little resemblance to Chain-Home's fixed antennas. But the principle remains the same. Send out energy, listen for echoes, build a picture of what's out there. And the strategic logic that Dowding understood still applies. Information and awareness matter more than raw numbers. The force that can see the battle developing and respond intelligently has an advantage that numbers alone cannot overcome. The radar story is ultimately a human story. It's about scientists racing against time to develop new technology, operators staring at screens hour after hour, watching for threats, politicians making difficult decisions about when and how to deploy new capabilities, soldiers raiding enemy positions to steal intelligence, citizens enduring bombing raids that radar both enabled and defended against. It's a story without simple heroes or villains, a story of technological innovation that saved lives and ended lives, of strategic brilliance and strategic bombing, of defense and destruction so intertwined they cannot be separated. The controversial radar that exposed Nazi war plans didn't just detect aircraft. It detected something deeper. That modern warfare would be won or lost through technology, information, and the ability to adapt faster than the enemy. That lesson, learned in the skies over Britain in 1940, remains relevant in every conflict since. In the end, radar was just radio waves and mathematics, electrons and echoes. But in the hands of people fighting for survival, it became something more. It became the invisible shield that stood between civilization and darkness. And that frozen morning in 1935, when Robert Watson Watt saw that first blip on a screen, he didn't just detect an aircraft. He detected the future. A future where information would matter as much as firepower, where awareness would multiply force, where technology would transform what was possible in war and peace. The radar revolution that began in that frozen field continues today in ways both visible and invisible. Every time you check weather radar on your phone, every time a plane lands safely in fog, every time doctors use imaging technology to diagnose disease, you're benefiting from technology born in desperation during humanity's darkest hour. That's the legacy of radar. Not just that it won the war, though it did, but that it transformed our relationship with technology itself, proving that scientific innovation could be the difference between survival and annihilation, between freedom and tyranny, between knowing what's coming and flying blind into the night. The controversial radar that exposed Nazi war plans exposed something else, that in the modern world, knowledge is the ultimate weapon, and the side that sees clearly will defeat the side that gropes in darkness, no matter how powerful that darkness seems.